So let's get started. Well, it's my honor to introduce three of our outstanding students who worked on problem C, dog cannot catch a treat. And their talk title is Using Differential Equations and Artificial Intelligence in Modeling Fritz. Let's welcome Lillie, Nathan, and Mark. Thank you.
Hi, everyone. Thank you for this awesome opportunity to present. We're excited to share with you the methods that we took to model this problem. So, hello, we're team 1148 from Penn State University, the Berks campus, presenting on problem C from the SCUDEM 2023 competition. My name's Nathan.
I'm Mark.
I'm Lillie.
All right, and our presentation is titled Using Differential Equations and Artificial Intelligence in Modeling Fritz. So I'm just going to start with an overview. We're going to begin by kind of just introducing the problem in case you're not familiar with it. And then we're going to head into a discussion on our initial brainstorming process, which sent us into the differential modeling of the food object. And then we'll step into some general assumptions, how we decided to model Fritz, the dog. Then we'll show some code, our results, and then lastly, end with our conclusions. So this is Fritz. The problem we were presented with centers around a video of a dog named Fritz who struggles to catch various food objects tossed by his owner. So the goal through mathematical analysis was to determine if Fritz is simply clumsy and cannot catch the food, or if his owner is being intentionally mean by tossing the food in ways that make it difficult to catch. So our initial brainstorming process began with kind of several general mathematical ideas. So we began by looking at the problem from a probability standpoint. So one of our initial ideas was seeing if we could model Fritz as a three-dimensional probability density function, kind of under the idea that is there a specific probability value in three-dimensional space where the food is and Fritz catching that. So as you can see on the slide, I just have an example of a 3D probability density distribution. And kind of our idea with this was that if we could come up with a 3D probability density model, could we then use methods from multivariable calculus, such as arc length parametrization or line integrals, and calculate the total amount of quantity that a trajectory of a flying object passes through this probability density function. And the kind of idea was behind this was that if we could calculate the probability of an object flying through Fritz's probability density model, we could come up with an optimized probability density model for a dog that can catch. And then we could quantitatively compare the probabilities of Fritz catching this object and the dog catching this object. So I also have an example of an arc length parametrization integral, except this is over 3D space, where we would parameterize the trajectory of the flying object using parameters x, y, and z. So this discussion carried on for some time, but ultimately it led us to kind of focus on the idea of Fritz being represented by probability, which we transitioned into an AI model, and the trajectory of the flying object being represented by solutions to differential equations, which I will go into next. So before we dive into the differential equations themselves, we need to address the idea of air resistance. So shown here, we have the general ordinary differential equations of kinematic motions without air resistance, the acceleration in the y direction being the acceleration of gravity, and no acceleration in the x direction. However, when we add air resistance, the differential equations become nonlinear and are affected by many constants, resulting in a more complicated set of kinematic equations. So we plotted these solutions in Mathematica, as you can see on the slide, and we animated the changing variables of mass, shape, and velocity. So since the differential equations for kinematics with air resistance were nonlinear, we solved and plotted the results in Mathematica. For all of these plots, the arc that is furthest represents the object with no air resistance, and the inner arc represents the trajectory of the object with air resistance. The first plot holds all variables constant except mass. The second plot holds all variables constant except the shape of the food being tossed, and the final plot varies the initial velocity of the toss. So as you can see from these plots, changing the mass, the size, and the initial velocity of the toss result in different trajectories of the object.
Moving forward for our final model, of course, we had to make some assumptions that we're going to carry through the model. The first assumption that we made was air resistance was going to be neglected. Since every food object and velocity and different starting height was going to change the actual trajectory of the model, we decided to neglect it and could be added later depending on what type of food object we would be modeling moving forward. Launch angle will remain constant, so we could be able to create a model that the AI could follow as it was thrown. Motion and the model itself will be restrained to 2 dimensions. It's just made actually simulating the food object and Fritz itself a little simpler. And finally, we decided to not model wind since wind was going to change each throw and was going to add some randomness to our final model. So the general model the AI will use will approximate the motion of Fritz as a 2-link robot. Next slide, please. Thank you. The general model the AI will use will approximate for the motion of Fritz will approximate Fritz as a 2-link robot. Since Fritz rarely moved his feet from an initial position in the video, we fixed the position of the base. The system was also modeled in 2 dimensions. The reasons for this were the simplification of the model while still providing useful information. Also, the more complexity built into the model, the longer it will take the AI to train. This causes longer lead times for results. The resulting model is shown on the left. The position of the dog's head is based off of 2 angles, θ1 and θ2. The kinematic equations for the movement of Fritz are also shown. We restricted the domain of Fritz by restricting θ1 and θ2 to represent more realistic biological restrictions. The inverse kinematics for moving a dog to the specific point were also derived down and shown. So these are the general assumptions we made for the final model. So there are kinematic equations that we used. Again, there's θ1 and θ2, and computing a derivative with respect to time allowed us to find the general motion of the dog itself based on the derivative of x and the derivative of y. So for the artificial intelligence implementation, we decided to use the NEAT algorithm, which stands for NeuroEvolution of Augmenting Topologies. The way this algorithm works is it takes defined inputs from a user, assigned weights to each of these inputs, and then uses an activation function to determine whether or not to produce an output. The number of inputs and outputs, as well as the activation function, population size, fitness function, and the max number of generations are defined by the user. This is the ultimate machine learning and AI algorithm we will use to produce our final model. Now, in theory, creating this model is a lot simpler than in practice. Here's a slide showing some of the work in progress failures as we attempted to adapt what inputs to feed the model to best represent Fritz. Could you play the video? So the first one on the left will show the model before we implement domain restrictions. The model just went crazy, and of course it decided to spin 360 degrees around, and the AI didn't have any restrictions to follow. The second video is before we gave the AI model the correct inputs for which to follow for the thrown of the ball. Again, these are before we reached a final model, but as you can see, the AI doesn't know what to do with the inputs that it is getting from which we defined at that certain point. And that happens for some time. I think we're good on that one. So the values we decided to give the AI model are as follows. For inputs, the final model, we gave the AI θ1 and θ2 of Fritz, the distance between Fritz and the food X and Y position and time. For the outputs, the model told us whether to increase or decrease the value of theta 1 and theta 2. We use the hyperbolic tangent function as our activation function, since with that specific function, as the results tend towards one side or the other, they will quickly approach 1 or -1 to determine whether to move left or right. Our population size was set to be 100 per generation. The fitness function was created to reward the AI for catches and to punish the AI for misses. We also implemented the fact that if the AI was getting closer to the ball, to the food object than previously, then it would also get rewarded for doing better than it previously had. And we let the model run for approximately 500 generations. So here is part of the code. Here's the first half of it. This code was based on what we based the model off of. It was written in Python and amounting to about 250 lines of code to make the AI model. We had to code the model in such a way that each iteration of Fritz was in its own class, and we could simulate 100 Fritzes in each generation. And here's the second half of our code finishing up the entire script. So here's the first implementation of the AI model. This is at the beginning of the model itself. As you can see, is the dog so happens to want to turn theta 2 to be 90 degrees. As this is let run for longer and longer, it starts to come up with more complex iterations where it no longer decides to stick theta 2 to a fixed value and only fix theta 1. And as you can see, the model gets better. It will get better and better the more generations we run. That must be about generation 5 or 10.
So after we had our basic model, we started modifying the variables. So for the food, we varied the velocity and the starting position. So that way, you're not doing the same exact throw every single time. The dog has to adapt to that variability. For the dog, we changed how many iterations they were given to learn and how many dogs existed in one iteration. That basically just lets us test how our model is actually working. And then for simplicity, we also added in some additional assumptions. We said that the food would be catchable, so that way Fritz isn't punished for a bad throw on the owner's end. And we also said that once the food dropped on the ground, then the dog couldn't pick it back up, so that way he's not being rewarded if he picks up the food but doesn't actually catch it mid-air. So after running multiple simulations, we found that our AI model learns more slowly when we change more variables. So in this graph, each simulation is a different color. And on the x-axis, we have the number of iterations. And then on the y-axis is how many catches. So as you can see, in the blue group, the number of catches increased the quickest. So this means that the dog learned the fastest. And this was with constant initial velocity and constant initial food position. So basically the same throw every single time. Then in the orange, we varied the initial velocity, but kept a constant initial position. And as you can see also, the learning was slower, but it eventually was able to catch up to the blue. Then with the gray, we kept the initial velocity the same, but varied the initial position. This one was worse. And then with the yellow, we varied both the initial velocity and the initial food position. And this group was not successful at all. And actually what happened was learning decreased. This actually implies, though, that our model was insufficient for handling multiple variables. So we don't count this to mean that Fritz is necessarily failing with this, but that it was some changes that needed to be made in our model instead. So then we can take those results and try to answer some questions with them. So first of all, how precisely does the dog's brain have to be in order to estimate the orientation of his head and eyes? So our AI model was created so that the dog's head had to have a hitbox of a few centimeters. and the food also had that same hitbox. And so basically, if those ranges interlap, or overlap, sorry, then that means that the dog catch the food. Similarly, in real life, the dog has that little bit of wiggle room to catch the food. Next, how much time will the dog have to orient its mouth to the correct position? Of course, this changes with every throw as you're changing velocity. So it just depends on those initial conditions. For example, if the food is thrown with a higher initial velocity and high initial launch angle, then the dog will have more less time to catch the ball, or he'll have to have a higher, quicker reaction time. Then are certain foods more difficult to catch due to different effects of air friction? So of course, air friction is going to be a factor for the food. For example, we had shown earlier that mass, initial velocity, coefficient of drag for the food definitely affects it. Additionally, wind would affect this, though we decided to neglect wind for the simplicity of our model. But due to the wide possible range of trajectories that would change for each individual food, we decided to neglect air resistance. Another reason that we could do this for our model, though, was because we were working in smaller ranges of velocity and initial position. With wider ranges, this would definitely make a difference. And we could also easily incorporate this if we were working with one specific food. Next, does the height at which the object is thrown matter? We see that height and velocity definitely play a part. With increased velocity and with changing launch angle and changing initial position, the dog has less time to catch the food. And if they're varied from throw to throw, then the dog also learns more slowly, but he might be able to catch up to the dog that's catching the throws that are kept constant. And, oh wait, yep, okay. Next, what are the most important aspects of the dog's perceptions and the behaviors for the dog's success? So the most important factors that we saw, and this was just based on trial and error, but we saw that the most important aspects were the distance between the food and the dog, and also the time that passes between the throw and the catch. However, with enough iterations, the time actually ended up not being as necessary. It just meant that the dog took longer to learn how to catch the food. And finally, use your analysis of this situation to decide if Fritz is just clumsy or if his owner is being mean to the dog. So with all of this in mind, it seems that the best way to make Fritz look bad is to just not train him, because as we saw with each training or with each iteration, Fritz learned how to catch the ball better. But if his owner would want to make more videos, then he should only throw the food to Fritz when the camera is rolling. Additionally, the owner should throw the food so that it's just within Fritz's range of motion, so that way it makes it more difficult for him to catch. So overall, even though the owner could make Fritz look clumsy, we still do conclude that Fritz is clumsy on his own, because in our model, the conditions for Fritz to catch the food were optimal, but he wasn't able to catch it all the time. However, this outlook could change in a more complex model. So moving forward, there are always improvements to be made. So here's what we would do differently next time. First, we would improve the model so we could incorporate multiple variable changes. That way, we could change or better change the initial velocity, initial position, and more variables, and the dog would still be able to learn, even if it would take longer to train. Secondly, we would delay the dog's reaction time to see just how bad it can be before he's not able to catch the food anymore. Third, we would introduce noise for different sized foods. So this would mean that it wouldn't matter as much what those variables for air resistance would be. Fourth, we would change the dog's dimension and mouth size. This would allow us to test what would it look like if we were testing different breeds of dogs? How would a smaller dog compare to a larger dog? Things like that. Next, we would add air friction inside the model. So this kind of goes back to introducing the noise, but if we wanted to test one single food, then we would be able to do that. And then finally, we would expand our model to 3D instead of just keeping it in the 2D version that we were working with. All right. And with all of that being said, we'd like to acknowledge the sources that we used. Thank you so much.
Thank you very much. This is really great talk. So do we have any questions from the audience? Well, I will ask my questions first. Oh, Sammy, do you have a question?
No, you go ahead. Go ahead.
Oh, actually, I'm just curious. So, are you all three of you math majors? I'm kind of interested in your training background and like that. I don't see my third year or fourth year math major student like probably not very good at all those programming and everything. So, I'm just curious, what's your training background before we move to something else?
I'm a mechanical engineer major.
Yeah.
All
Yeah,
three?
and I am as well.
And I'm
Oh,
actually
all three.
I'm a biochemistry major.
Ah, cool. So
Yes,
you've taken some like machine learning like courses by any chance, or?
no,
I
none of us had. I think, I know Mark and I had some coding background. Nathan, did you have any coding background before this?
I've taken some coding classes, but nothing really in machine learning.
Yeah.
Wow.
all
Wow,
my,
that's cool.
all my knowledge with Python was self-taught.
Great. Super impressive. Thank you. And yeah, Sammy, go ahead.
No, I thought it was very impressive, yeah, that you used a combination of AI as well as the kinematics and the differential equation model, and so I thought that was really cool. I guess my question is, in the AI model, how did you? I mean, because I assume it's some sort of deep learning model with hidden layers and some number of neurons in each layer, and I was wondering how you decided on constructing that model. How did you decide on how to construct the complexity of the model in terms of the number of hidden layers and neurons and that sort of thing?
So initially we started, of course, with no variables put into the model itself. So we had no hidden layers, and we slowly introduced more and more inputs for the neural network. So we started with, of course, the angle of the dog, the distance that the food object is from the dog, and adding, of course, initial velocity so the dog would be able to determine. And then we added two hidden networks, well, two neurons within the hidden network to allow for a little more complexity in the model. And then, as you saw by our results, we got the model to a point where the model wasn't perfect because that wouldn't represent a dog in real life. We got it until it was just good enough to where we could see learning, and over time the model got better and better rather than just being random objects moving around.
Yeah, that was very cool. And you showed one condition. I think it was where the velocity and initial position was changing, and in that case, over time, the dog was actually making less catches, right? So how would you, I guess, what's in your future, like, I know it's a very short-term project, but if you had to improve your procedure or your model or your AI, why do you think that it actually got less? How would you why do you think that happened, and what would you try to change to see if the dog is actually learning in that scenario over time?
So if I had to say why it got worse over time, was that our inputs weren't sufficient to be able to train the AI model. So in the other ones where we only varied one at a time, the dog was actually given those conditions, so that I would assume that the model was just assuming that, oh, theta is 30 degrees in this case. So it went to what it should do for that particular theta. But when we started varying two objects at once, it didn't have that same ability to learn and see that the velocity is this and theta is this, therefore do this. So that's what I would say. And to improve that, of course, let it run longer and see if we eventually saw an uptick in learning, or second, just give it more inputs to be able to try to teach it a little better.
Okay. Cool.
Any other questions? Well, I just want to, I know engineering students are big on doing summer interns. Because I think this is really good work. If you have time in summer, I really hope you continue the work and submit it to some like undergrad research journals with, if you can find a mentor on campus and, continue your great work. So I guess, thank you very much. And hopefully you're gonna join the SCUDEM competition again later this year.
What year?
Best
What
of luck.
year? What year are you all? You're all undergraduates.
We're
And
all second years.
second year.
Yep.
Okay.
Oh my
So,
God,
yeah, you
second
got,
year.
I guess two more competitions then, right? Maybe if you're
Yeah.
no, that
You're
was really impressive work. It's really great.
Yeah, I mean, it's already outstanding award. You have a very high starting point. I'm looking forward to more outstanding awards in the future then. Thank you very much. Bye.
Thank you.
Thank you.
Thank you.